please.
Yeah, so we are representing the BADGER Robotic Control Project from LeTourneau University. This is a big issue. If you've done any golfing, you're probably familiar with how aggressive geese can be, the mess they can make. And this is really a wider issue than just geese on golf courses. There's also, like, for example, airports, or really just in general, animals in urban environments. And how do we live together? How do we manage their populations in a way that doesn't detriment them, but also doesn't cause a whole lot of inconvenience? So, for example, like with geese specifically, the amount of mess that they make, some golf courses spend up to $250,000 a year cleaning up after them and trying to remove them. And so there's a market. There are some existing solutions out there, but each one has certain aspects that it doesn't quite meet of what we think would be ideal. So, for example, if you use dogs trained to chase them, then you have the dog. You have to pay for the trainer. If there's any injuries or medical expenses for the dog, all of that can add up quite quickly. If you use a noisemaker, that may chase the geese away, but also negatively impact other endangered or protected animals. Likewise, if you're, for example, trying to perfect your golf swing, having noisemakers is kind of distracting and annoying. The Gooseinator robot, it's one that's also been designed, but that's a manual control, so you have to have an operator still doing all of that. There's also a green LED system because they've found that geese don't like green lights. But that, again, those are stationary systems, doesn't give you mobility. There are some other options, ultrasonics, or you could possibly find an application with something like the Spot robot by Boston Dynamics. However, the guesses at what that'll cost once it's commercially available are at least $10,000. So that's quite an investment, and we wanted something that was low cost. This project was sponsored by A&K Systems, and actually their CEO was supposed to be here, and thanks to the weather, he's currently in Denver. And anyways, so they sponsored our project, and we're grateful for that. They do mostly software for the pest control industry, and working with their clients, they saw this need for detecting geese and chasing them off of golf courses. But they're not a robotics company, so they got involved with LeTourneau University and made that partnership. Some of the requirements we had for our robot is it needs to detect geese from a variety of angles, not just from a certain profile, and also not misidentify some other animal and try and chase that. We also want it to drive its entire route autonomously rather than having someone controlling it. And amphibious also is important because, well, first to back up, we didn't do a drone just because of the range and getting the battery size. There's a lot of things there that it just made more sense to go with a land-based system. And by making it amphibious, the geese no longer have a safe space out on ponds or lakes. And so that just gives one more way that we can pester them. So then going back to autonomous, if we can charge it autonomously, that means you don't have to send someone out there each night to plug it in. And then also the collision avoidance, you can do some of that just by making your route to go around buildings and trees and such. But it's also useful to have that for if there's a golf cart that's parked somewhere, or you don't want it to run into the geese as it's chasing them. And then also we want it to connect to the cloud. This is something especially important for A&K Systems because they do a lot with data collection. And so we take a picture of each animal that's chased, and then that's uploaded. You can look in a Google Drive folder to see whether it's actually chasing geese. A few other specifications we had for it. It needs to be able to drive at least 5 miles because you've got a pretty large area to cover with a golf course. We also wanted to be able to detect geese at least 5 meters away. We wanted it to be waterproof, at least IP67 equivalent because of going in the water. We wanted a communication range between our base station and the robot of 2 miles because we've got some radio communication going there. We didn't want it to be too heavy since this needs to float, so we set that at about 70 pounds. And our prototype materials cost for this first one that we've made needed to be under $5,000. So this is the robot that was built last year. And a quick summary, this is the block diagram of everything going into that. We use a Raspberry Pi for our main computation as well as some neural compute sticks. You can see also a few of the other sensors we have on there, the battery powering that, and then on the right side, some of the electronics that are in the doghouse. First thing that we needed to decide upon was how we were going to propel our robot. We looked at a few options, and we decided that using tires and then propellers for the water would be the most efficient. So once we knew that, we were able to select the motors for that application.
Oh.
There we go.
Yeah, so in our motor selection, usually when you're going through motor selection, your biggest focus is peak torque, what it can output whenever it needs to. We actually found that our main issue was not that. Our main issue was efficiency. When you're driving for long periods of time, your battery size is determined by how efficient your motor is, and we were having a more negative impact by having a inefficient motor because it made a bigger battery, and therefore you had to have even more torque. So our torque was more impacted by our efficiency than the actual torque value. So in order to actually test this rigorously, we went out and we created a rig by which to test rolling resistance on different surfaces. So tall grass, short grass, concrete was obviously very smooth. And then we did, that's a trend line of different weights and how the weight changed our rolling resistance. Based on that, we chose our motor. So we went with a brushed motor. Unfortunately, there were no, brushless is way more efficient, but there were no brushless in the size range we needed to get the torque value to move a 65-pound robot. So as you can see, this is the torque curve of our robot, and we're operating at 60% efficiency, which is actually pretty good for a brushed motor, and is very close to its maximum efficiency, and that's what we were focusing on, and it does meet our speed and torque requirements. So after we had our motors, as those are our main power draw for our robot, we were going to size the battery. We wanted rechargeable, lithium ion, and we went with this battery. This battery is normally used on electric bikes to make a normal bike into one that runs on electricity, and so it gave us a good weight to power ratio. When actually testing, we found that we went a little overboard on efficiency. We did not have a 5-mile range, we had a 15-mile range. Sent it back and forth between 2 GPS points over and over, and yep, that's where we got to. Voltage does drop and it does slow down over that time, but it is able to still meet some minimum torque requirements at the end of the test. So with that, we'll move over to how the motor is actually driving the robot.
Yeah, so being outdoors, there's a lot of terrain types that we could encounter. We wanted 4-wheel drive for this, so we were going to do one motor for each tire, but to minimize our weight and our cost and also just placement of things, we instead went with 2 motors, one for the left, one for the right, and then each motor has 2 chains for each of the wheels it controls. So that provides us with tank drive. And then it also allows us to move the motors above the water level, making waterproofing that much easier. The water line will end up being about at the top of that blue foam. Our chassis design, once we knew our motor and our battery, since those are the largest things, we designed that out of aluminum. That is lighter and less corrosive than steel, but it is much cheaper than using titanium or carbon fiber. This is what our final design looked like. Just as a note, that's not something that would need redesign for mass production, but for a single prototype, that was the best design we had. So we've talked about the variety of terrains it covers. There it is, driving into a pond. It's also able, if you've got something like a flooded walkway, to take care of that. And then we did a test. Hopefully you wouldn't actually encounter this on a golf course, but it is able to handle some pretty rugged terrain. That highlights, though, how important it is to have a waterproof robot. To do that, we separated the motors from the rest of the electronics, since it's so difficult to waterproof around a shaft. And then we had all of our electronics in an off-the-shelf IP67 rated box and used cord grips, which are fairly standard across the industry, and tested each of those, holding it in the water, so that we know the brains of our robot aren't going to get leaks in there. Our motor housings, we wanted to do acrylic tubings because then you could see the leaks without disassembly, but that's a lot more expensive, and we're keeping this low cost, so instead we went with PVC. And then our propeller motors, those were submerged, and so that was the most difficult thing to waterproof, and it is still not perfectly waterproofed, and so that is something for future work that's not quite to an IP67 equivalent rating, but it is much higher. You don't have to go disassemble them after each run in the water. And that's a fairly common approach with RC boats, using a stuffing tube filled with grease. And we also did tests to find what was the best grease that would not wash out of there and maintain that seal for the longest time possible. For our flotation, initially we were going to do pontoons on the outside, but that would be difficult to mount and makes it larger than it already is. So instead we filled the underside. We calculated that would give us enough buoyancy, and when we actually tested it, it did. And then we coated that with plastic and a layer of spray-on rubber Flex Seal, so that as you're driving over, if there's a stick or a rock or something, that's not going to tear up the foam and lose your buoyancy. So it has some features on it. This is a large robot. It needs an emergency stop if it's running at something, as well as you don't want to plot every tree. So it has some time of flight sensors that can detect that and drive around those, as well as, just in case there is something we happen to miss, there's a bumper that it'll trigger and then back up rather than continuing. So that bumper, again, that's something that needed to be waterproof. Used IP67 rated limit switches and did some calculations to ensure that the drag force on that bumper in the water isn't going to trigger it and tell it that it's running into something when it's just water. So we didn't think it would go any faster than 5 miles an hour in the water, which would give you 110 newtons of drag force, whereas so long as you're going at least a mile an hour, you'll have easily 470 newtons of impact force. So going back to the autonomous aspect, it's important to have the doghouse. That's one less thing, the stuff that it does, so that you don't have a human intervening every day. In there you can see some of the electronics of how it uploads to the cloud, as well as some of its communication. And then internally, it has charging. It has plates on the outside that when it drives in will scrape against those brushes, which cleans off anything that may have accumulated and provides charging similar to the way that a bumper car, which has usually they have like an antenna going up within a brush touching like something along the ceiling. And so it charges in that same way. And we had initially considered inductive charging, but this is more efficient, and there also is not anything in our size range readily available.
Yeah, so moving more towards the software aspect of our project, one of the first things we designed that was very, very useful was our graphical user interface. So we made this user interface in Python language, and it gave us just basically an output for the robot and an ability to interact with the robot without having to just use a straight terminal. We were able to see where it thought north was, roll, pitch, yaw, all those things, errors that it spat out. We were able to change it from manual to autonomous mode. You could even drive it and drop GPS points and create your own path on the fly, which is very useful for testing in the field and not having to lug a computer around with you. So, this was the route that we went with. It's on Laterno campus, but if you could look, it goes along the road at multiple points, and down there in the kind of left towards the U shape, it actually is going through a pretty decently small gate, at least for a robot, which is pretty difficult. Here it is doing that course, driving through gates, going on different terrains, and it's able to do all this within a margin of error of about 20 centimeters. Here it is doing similar thing on water, making figure eights around 2 GPS points. So how did we achieve that kind of GPS accuracy? We used a real-time kinematic GPS correction. That correction allows you to place 2 GPSs, one of them inside of the base station, one of them inside of the robot. As long as that has communication between them, the base station, knowing that it is not moving, sends corrective messages to the robot and says, hey, GPS satellites are telling me I'm a foot to the left, but I know I haven't moved, so you're not a foot to the left either. So for our control system, we used a basic state machine hierarchy with different priorities. So our first priority, if you take manual control or you press the emergency stop, it stops doing anything else. If you are entering or leaving the doghouse, so it's driving along and it's decided I need to charge, it will not try to chase geese, it will not try to follow its path, it goes into the doghouse. Next priority is the collision avoidance. In case we are driving along chasing a goose and wind up hitting a tree, it needs to know that it needs to avoid obstacles more than chase geese, and then following the path. And if you don't have a path currently loaded, you just turn on the robot, it just idles, sitting there waiting for instructions. So here it is doing daily scheduled patrols. So it exits the doghouse and on a schedule. So you set the times that you want it to come out. Ideally, we would have these times be kind of towards morning and evening when the golfers aren't there, but the geese are specifically wanting to nest. That's when you want to drive them away. So it also comes back and auto docks itself for recharging and uploading its images. Speaking of that, yes, it does upload images of everything that it is about to chase for two very good reasons. First, these are specifically the golf courses we were designing for were around A&K system in California, and they actually have other birds that are there that they don't want chased because they are endangered or they live in the area, and we don't want the robot to chase those. Another very good reason is that it helps us to train the neural network. So our model is very good, but a model that was actually built for that specific golf course with images that have that golf course in the background would be even more accurate. So we have the camera is mounted in a little rotational turret. It doesn't rotate super far, a little less than 180 degrees, so that it is able to see where it's going, though it doesn't use that for obstacle avoidance. We made it to where it is waterproof itself, and the lens is slightly forward because as the presenter on signs mentioned, whenever there is water obscuring it, it makes it useless, and so hopefully that'll have the water roll down instead of beating up on it. So the first network we went with, not actually a convolutional neural network, we went with a basic Haar cascade. It's like a single node from a convolutional neural network. And it's moving pretty slow because this is running on the Pi's processor. But our issue that we found, here's it identifying things. And you notice it doesn't pick up every goose. And the reason for that is it's able to detect lines really well. And so it detects side profile geese amazingly well. It's horrible at them at any other angle. The moment the geese start running away from it, they're facing its back to it, and it loses all interest and leaves, which is not ideal, as it's supposed to chase the geese. So we looked at other options. We eventually went with, a convolutional neural network running as well on YOLO v3, though we went with the tiny version. And as you saw, the Haar cascade was running slow. This is made up of a bunch of Haar cascades running in nodes. So we had to upgrade our hardware. These are two different neural compute sticks made by Intel that are running our trained AI on them and just giving the basic vector information to our Pi. So here it is running. That's real time. It's able to see the geese from all different angles, and it reacts quite quickly to them as well, though we do have a little bit of latency. Even though it's real time, it's just got a little bit of time in between. So here it is, live test. We have a goose decoy, and we turned off all of its safety features because we just wanted to see it hit the goose. And so, that's it moving from navigation to chase goose, and it ran the goose over. So here it is actually removing geese from a golf course. Unfortunately, this is our only test because we had trouble finding geese on golf courses. And when it chased these off, they left, and they left forever, and we couldn't find them again. So that's our one live test, which is something we would like to work on in future. Speaking of which.
Yeah, to sum up the goose detection with our current network, we haven't had any false identifications, so far good on that one. And we've also, as those videos demonstrated, it's able to detect a variety of angles, unlike the Haar cascade. The driving is also autonomous. It's able to complete that entire route on its own without someone using some kind of game controller. And it also drives in the water. That is something, we have some future work. We want to improve that. Not all aspects of the robot are up to IP67 rating. So there's some redesign work there going forward. Collision avoidance also, that as you saw demonstrated in the video, if it's turned on, it'll also avoid the geese, like it did the tree in that one video. And then the cloud connectivity, like I said at the beginning, it'll upload to a Google Drive folder that someone could check from their desk rather than going out and plugging in a USB or something. Our driving range was well above 5 miles an hour, which means you could do multiple rounds without having to recharge. And then also the goose detection range, we were just over 5 meters away at where we could detect it. And the waterproofing, again, not quite up to IP67, but it's definitely, as far as prototyping going, it was to a point, and we also used marine motors for the propellers. So that wasn't a hindrance for the prototype, just something that a mass-produced robot would need improved. And then the communication range with the radio for the GPS, that was 2 miles. We achieved that. Our weight ended up being around 65 pounds, which we were able to float quite easily. And that was also because it was a wide robot. Even though our battery and motors were up high for our center of gravity, that's not ideal, but it was wide, so it was fairly stable on the water. And then we were able to keep our materials cost under $5,000. Yeah, so future work, one thing with the entering the doghouse, it is able to do that using GPS. However, we believe it would be much more reliable to use computer vision, as the GPS is very accurate considering that you're using something out in space, but we need it to be more reliable than that. And we could also work on improving the object recognition. And we also want to do more tests with, are the geese going to get acclimatized over seeing this robot multiple times? Will they get used to it? Do we need to do something other than just drive faster than their walking speed? Waterproofing, again, also improved, and geofencing is something that we expect would be implemented in the future, so that something like a sand trap or where there's reeds in the pond, you just avoid that entirely, so that the robot isn't dealing with that.
Yeah, so we'd like to thank, of course, A&K System for sponsoring the project, and the very, very committed team of undergraduates, including myself and Emily, who worked on this project last year, and there's another group that is working on it this year, and they're doing well. I'd like to also thank Dr. Hu Kim, our direct senior design lead, and and Dr. Junwan Kim, who was helping out with leading the team as well. And so, yeah, questions. Yeah.
So yes, I'm curious, what kind of telemetry are you getting back from the vehicle?
As in, sorry, what do you mean?
What kind of telemetry are you getting back? In other words, for example, health status?
Yeah. Okay, so we have basic information on things like, am I moving still? So I think I'm moving forward. Am I actually moving forward? Does GPS indicate that? We have information coming from the motors to make sure that they are, in fact, moving, so it's not stalled out. We have information on if any of the safety mechanisms, emergency stop, bumper, LiDAR, when they were triggered, why they were triggered, things like that. GPS connectivity, some internal stuff. We wanted to add temperature sensors. That may be something we do in future. For now, not yet. Yeah.
Any temperature measurements, just out of curiosity?
We did do temperature measurements physically on it, and we had no, because we were worried. Anytime you waterproof something, it's thermally isolated as well. So we did do tests and determined we didn't have a problem. It stabilized at a reasonable temperature, well below any of our components requirements, but it would be good to have constant temperature monitoring anyway, just to confirm that test.
Just you mentioned that you had only one field test.
Yes.
Yeah.
The geese as unknown as aggressive creatures.
Mm-hmm.
Yes.
Is there any plan that maybe to protect the equipment, they might come and damage your camera or antenna?
Yeah, so we did a lot so far as ruggedization. There's, I think, especially with the sensors, the antennas on the back, ensuring that those are not going to get knocked off if a geese decides to attack it. And yeah, like you mentioned, we were only able to do one test because by the time it got to that point, it was far enough in the year that a lot of the geese had already migrated. So going forward, that's definitely something that needs more testing.
One useful thing we did find out, though, is that they're not actually that aggressive before nesting season. So when they're trying to find a nest, they're not very aggressive at all. They're willing to move locations and stuff like that. It's once they've picked a nesting site. So if we can implement this robot running around before they pick their site, they're much more easy to just get to leave.
So they might eventually get used to it?
We're not sure, yeah. We need to do some testing along those lines.
We do also have, there's a green LED in that camera turret, and there's also, it blinks somewhat randomly, so it's not predictable, but again, something we need to test how much of a difference that actually
Some
makes.
studies indicated that does something, so
Yeah.
we'll see.
I think there.
I just want along the same lines that you mentioned in your requirements, if you wanted to not detect other types of birds, were you able to test that?
Not
It's
other
hard to
types
get
of.
these birds to cooperate with your testing.
Yeah, no, it is. And also, people need to be working on this. There's a very, very small data set for thermal images of geese from different angles, and I feel like that's a problem. But we need more data to be able to confirm things like that. We were able to test it with other objects. We were able to test it with pictures of other things, but it's just not as good as having data of actual instances. Yeah.
Yeah, so how your robot is avoiding from obstacle? Is there any like a safety distance first you are giving it?
Yeah.
If you see the obstacle, what is the first reaction that is happening?
So it
Is
has
it turning right, left, or what's
Yeah,
happening?
it has 2 time-of-flight sensors that'll do the distance. And you saw there's one video where it's driving straight towards a tree. It detects that, and so then it's able to back up a little bit and go around the tree.
Yeah. Primarily, our obstacle avoidance method is GPS path, though. It will follow the GPS path that's preset, look for geese, and follow the geese. So the idea is wherever the geese go, it can probably go. But we do have some collision avoidance.
Just an observation on your verification of your requirements. If you go back to your requirements, right there. Okay, so just an observation is that you made yourself kind of stringent on your requirements. Like, for example, communicating in range 2 miles. That tells me exactly 2 miles, but you maybe do better than that.
Yes, we
Yes.
do.
You're probably looking at 2 miles or better. Everyone should have a greater than or less than.
Yeah.
Mhm.
So we set 2 miles as something that we thought, you think about the size of a golf course, that should be at least enough. But we haven't tested like how far. Like we tested the extent of the driving range, but not yet the extent of communication.
Yeah, because if you advertise better than 2 miles and you come up with 5 miles, you
Yeah.
go, whoa, this is great.
Our issue was it's harder to test than you'd think. We thought, oh, radios connect, they send information, bam, we got it. No, what we found out was beyond 2 miles, we started getting packet loss. And so it's not a hard to find, oh, we're not in range anymore. It's like, oh, we've dropped more packets than we usually do, which we send more than one, so that's fine. But yeah, it's hard to define when we're out of range. Yeah.
Go ahead. I just have comments. Go ahead.
Did your robot run into the doghouse a lot? Because when I looked at when you had the art system hierarchy,
Mm-hmm.
it was going home was above object detection, right?
Yeah, no. It does not usually run into the doghouse. It does this annoying thing where it kind of goes towards it, and then it decides nope, and it turns around, and it goes back, and that's more often our failure mode.
Also, inside the doghouse, there's a wider opening than the actual robot, and then it angles in a little bit to help position it.
Yeah.
Right
So if it
between
enters
those.
at any point, any angle, it kind of gets pushed towards the back. Yeah.
There is no time I can ask him at lunch. I don't have a question. As I was listening, couple of observations. So first question is, why robot? The problem you're trying to solve, why not a drone?
Yeah. So looking at our requirements for range, our requirements for ruggedization, looking at the battery requirement for a drone of that size, we would be moving into the same size drones they use in Hollywood for like carrying their cameras into the air. It would be a very large drone, and when you look at drones that size, they're usually gas powered and not rechargeable. So it would have a refueling station, and it would be flying around, very large, also causes a disturbance to houses and things in the area. We just didn't think it was the best option.
Congratulations on outstanding project. The second observation really is just to spur thought in your mind. I read a couple of days ago that in the United States, we have lost 40% of birds. I'm sure you read that story. 40% of birds have disappeared, which is a big biodiversity crisis in ecological systems.
Yeah.
So the question is there anything, no, you are only going after geese, which are, different kind of birds. But is there any application that you can think of for your robot that would rather go the other way around and recognize different kinds of birds to protect them rather than get rid of them?
Yeah.
You could
Let's
possibly,
think about that problem.
yeah.
Yeah.
At the very least, you could use it to patrol and observe what birds there are.
And
Yeah.
take images and document
Yeah.
their
Yeah.
behavioral habits and things like that.
And our goal isn't just to get them to go away, it's to get them to go to a different nesting
Right.
site where they're not in the way of people and people aren't in the way of
I could
them.
imagine that
Yeah.
technology could be used for the other.
Oh,
Definitely,
yeah.
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 There's once you have the platform, there's a lot of things, agriculture or so many different industries that you could apply it to.
Yeah.
Thank you.
Good?
Glad to know that.